Hello everybody, it's Coach Tapman, and today we're going to be talking about moments. So what is a moment? Really, it can just be thought of as torque. In physics, a moment is an expression involving the product of a distance and a physical quantity. Really, in our consideration, torque is the product of a distance and force. And so it can almost be thought of like a rotational force. If you apply a force some distance away from any reference point, what you would be experiencing is rotation. And you understand this. This is how a door works. You're pushing on a door some distance away from the hinge, and it makes the door rotate about the hinge. And so the closer you are to the hinge when you actually apply a force to the door, the more difficult it is to open the door. While the farther you are from the hinge where you're applying your perpendicular force, the easier. That's because your moment or your torque is greater the larger your distance from that reference point is, or your fulcrum in our consideration for a door. And so it really can be thought of as a rotational force. That's not technically correct, but it's a way to understand it that makes sense in our heads. So how do you calculate a moment? What does that actually look like? Well, it's fairly straightforward. A cross product of a force and a distance gives you the moment. Technically, it's the cross product of the radius times the force. And there's different units for that. That can be Newton meters, that can be foot pounds. And it's calculated with regard to a reference point, and you are in charge of choosing your reference point. So, in the example of the door, you're creating some rotation, the distance from the axle of the door. You could also figure out the rotation or the moment about some point in the middle of the door. You could even calculate some rotational moment to the outside edge of the door if you wanted to. Technically, there's torque being applied all over the door when you apply force anywhere, and we can see that here in this example. So we have this beam with points A and point B, and we just have this force F being applied somewhere between them. We don't know actually the distances, but it doesn't really matter for the sake of this example. This force F now, being a distance R1 from A, this force F perpendicular to that distance from point A will cause a moment or torque about point A. It will cause rotation about point A. So to calculate that, we would have the moment is equal to R1 times our force. And you can think about it like this. If this force, let's just assume that it was a person, and you took a rope and tied it to that person from point A, and you told person F to just continue walking in the same direction they're pointing. They're going to rotate about point A, some fixed distance. And that's kind of a way that we can think about our moment, is it's really causing a rotation about some point. So here we have R1 times F creates a clockwise rotation about A. Alternatively, that same force at a distance of R2 from point B is creating a counterclockwise rotation about point B. And so you can see here a couple things. One, a single force creates a number, an infinite number of moments about some object that has physical dimensions larger than 0, right? And so you can have a moment about any point on this beam. It doesn't just have to be A or B, but you can have an infinite number of moments due to this force F because our beam here has dimensions. And so that's good for us to know. That means that a moment isn't just a single thing that acts on an object. It can be you can calculate a number of moments, which will be useful later, as you'll see. It also tells us that there are two different directions, and so we need to decide which direction is positive. Because what if you're calculating a rotation about some point A that's clockwise, and you have another rotation about A that is counterclockwise? Well, how do you add those together? One of them has to be positive, and one of them has to be negative, right? Well, traditionally, a force that creates a counterclockwise rotation is considered positive torque or a positive moment. So that's how we'll be doing our examples, but you can certainly set this how you want to. You have to be consistent though, and you have to also know that when other people look at your work, they're going to be looking for standard conventions. And so standard convention is that a counterclockwise rotation or torque is a positive torque. Okay, so let's look at this more in depth. So moments are vectors. And we like to consider moments as vectors because it lets us add them together or subtract them from one another. It lets us work with them in 3 dimensions. And it makes it very easy for us to do that, especially in calculations that use computers and things like that. So let's go ahead and look here at this example on the left. If you guys remember, a cross product is just your u times v cross product vector here, where you're getting the perpendicular product of u, this u vector, times your v vector. Right? And so u times v then is the cross product of vector u and vector v. In our scenario, in a moment, u would be your radius vector or your distance vector, or v would be your force vector, and u times v would be your moment. So if you look over here at this system, you have some beam that's just attached to some random point in space. It's just existing in space, and so we have some arbitrary reference plane, x, y, z, set up. You have our origin set right at this base of this whole arm. And what we see is we have a force being applied at the opposite end of our arm. And the distance to that force, the distance is this vector r sub naught times a. And so that means this vector, this radius vector, is at some angle theta to our force. Now remember, because we want a cross product, we are only interested in the perpendicular portion of that radius times our force. And so something we can do here, a bit of a trick, is we can figure out what portion of this radius is actually perpendicular to our force. And we can actually do that by taking theta and using our supplementary rules to figure out that theta is equal to or this angle here is equal to theta, and we can use that in our value for r sub naught a to figure out what the value for d is, and then we can multiply d times f to get this moment about our point 0. So this is our radius, d now acting as our radius, and f is our force, and crossing these two we get a moment vector. We can see here the cross product, this moment vector, this cross product would be pointing in this direction. It's important to note, though, that using the right-hand rule, we see that pointing in that direction will give us our rotation. Using the right-hand rule, our counterclockwise rotation about this vector. And so that's how we use vectors. We know that if it is pointing in this direction, it's counterclockwise about the direction that vector is pointing in. Alternatively, if this moment vector was pointing in the opposite direction, we would know that it would be counterclockwise about that vector. And so you remember, you want to point your thumb in the direction that vector is pointed, and that's where you're getting your rotation from. And so that's how we can look at moments as vectors. Why is that important? Well, we'll see here next. Something also important that relates back to that example we did earlier is, again, there's an infinite number of moments or torques being applied to this beam by this single force. And so the greatest torque is being experienced at the greatest distance away. And we can see that here. We have some beam sticking out of a wall, and when we apply a force upward, we can see down here, that's the location of the largest magnitude of torque exists at the farthest distance. And that makes sense. A torque is a distance times a force. And so you're just increasing your distance. Whereas the closer you get, until eventually you hit 0 when your distance is 0, the closer you get, the less torque you experience. Okay, so why did that whole vector thing matter earlier? Well, you can sum together vectors very easily. You can use vector addition. And so if you look at this scenario, if we have multiple moment vectors and they're in the same direction, or they're along the same axis, they can be positive and negative along that same axis, but if they are along the same axis, they can be added together using vector addition. And this is very simple. So here we have this sum moment, the sum total moment experienced by this whole beam here is equal to this moment 1 being applied over here at this point we'll call A, and this moment 2 that we're experiencing over here at this point we'll call B. Because these are they're along the same axis, we can go ahead and assume that they are two vectors that we can add together just using vector addition. Also, using our r cross f for our r vector and our f vector, we can calculate the moment about, we'll call it this point B, this r cross f vector is going to also be a moment about point B. And so we're able to calculate a sum moment by adding together this resultant moment from r and f, this moment about point B, and this moment about point A. And all of that sums together to create a resultant moment, and we'll call it x, here at this point B. Now the resultant moment would be different if we calculated the resultant moment down here at point A, because in that scenario, our radius to the force, the perpendicular radius to the force, would be 0. And so in that scenario, we would not have our r cross f, because our r cross f would be equal to 0. And so the resultant moment at point B is different than the resultant moment about point A, but we are able to calculate resultant moments of our entire system. And if our resultant moment is equal to 0, we know then that our system is not rotating. Whereas if it is not equal to 0, we know that our system is rotating. And that's just what we cover again here. If multiple moment vectors are in the same direction, they can be added together using vector addition. The sum of all moment vectors for a system will describe the rotation of a system. And a sum of moments greater or less than 0 indicates that the system is experiencing some rotational acceleration. It means it is rotating. Well, why does that matter? Well, we'll be able to figure that out later on when we talk about how statics works. But this is really useful in describing a system and the kind of movement and motion that it's experiencing. But first, we're going to do a quick practice with moments. So we want to find the resultant moment at point A. And so now we're calling this point A. We switched that up on you guys, but we figure you can handle that. About the point A, we are going to calculate the resultant moment. So I'm going to give you guys a few moments, and you guys are going to be able to work amongst your by yourself or with a partner, whatever you guys are doing, and try to calculate that sum of the moments. And then go ahead and pause the video. When you come back, I'll show you how to solve. All right, guys, welcome back. We're going to go ahead and look at the result and the solution to this problem. So it's fairly straightforward. The resultant moment vector about point A is going to be equal to moment 1 plus moment 2, so 10 Newton meters plus 50 Newton meters, plus we have our radius vector and our force vector, and our cross product of the two, because they're perpendicular, is going to be 10 meters times 50 newtons, which is going to give us a total of 500 Newton meters. And then adding together our 10 plus our 50 plus our 10 times 50 will give us a resultant of 560 Newton meters. And so it's fairly simple to calculate the resultant moment, and we know in this scenario then our object or our system will be rotating, because there is some resultant moment that is greater than or less, or that is greater or less than 0. And in this that means in this scenario that we have a rotating beam. And so, as you can see, moments are fairly simple, but they just take getting used to when it comes to looking at the perpendicular range times force, and just getting familiar with how to calculate the cross product using, whether you're using vector multiplication or using trigonometry. But if you guys have any questions, go ahead and leave those in the comments below. We look forward to seeing you on the next video, and hopefully you guys were able to learn something interesting. So thank you, and have a wonderful day.